Alright, so here's the third and final part to this. What does the scale read when the elevator accelerates downward at 6 meters per second squared? And so again, we have that student standing in the elevator, but now this time that student is going to be accelerating downward. So we still have the same free body diagram as we had in A. The force of gravity down and the normal force up, and the normal force is the reading of the scale, but now it's accelerating downwards. Come over to Newton's second law, sum of the forces equal to ma. So we have F and the normal force minus the force of gravity is equal to ma, where the normal force is equal to ma plus the force of gravity, just like we used in the last problem. Okay, so we look at that last problem. We're going to be using the same equation that we did in that last problem. All right, now let's plug in some numbers here. Okay, remember the mass of the person was 71.4 kilograms. The acceleration is 6, but this time it's downward, so we need to make sure to put in a -6. And then the force of gravity, or the weight of the object, was 700 newtons there, right? So now let's solve for the normal force. And 71.4 times -6 is -428.4 plus 700, and that gives us 271.6 newtons. So that's what that scale is going to be reading. It's going to be reading that force right there. So it's going to be reading less. It seems like the person is weighing less as it accelerates downward. And you feel that as you go downward in an elevator. Right now, if the scale reads 350 newtons, what is the elevator's acceleration? Well, if it originally started out at, if the person was weighing 700 newtons, and now it's weighing half that, well, we have to have half the acceleration of weight, so it would be half of 9.8 or half of 10, which would be around 5 or 4.9 meters per second squared. So we can do that without really doing the math, okay? And that just comes from weight equals mass times acceleration. Well, to find the acceleration, we just go weight divided by mass, okay? And so when we do that, we know that the weight of the person was originally 700, and we divide it by the mass, 71.4. So 700 divided by 71.4 gives us 9.8 meters per second squared. Okay, and that was the original acceleration of the object. And for some reason, my pen's not writing right there. Okay, there we are. Meters per second squared. Now, what happens if we have half the weight, 350? We still have the same mass, 71.4, and what do we get if we take 350 divided by 71.4? Well, we get 4.9 meters per second squared, and there it is to you, there it is mathematically for us. Okay, that's a simple way to solve it. We're going to kind of skip that number 8 problem for right now, but let's look at the statics one. Okay, so if the person is pulling on this with 300 newtons of force, what is this going to read? Well, that scale, this reading would say 300 newtons of force. So our answer for this would be 300 newtons of force. Pardon my pen, it's just kind of malfunctioning a little bit, but 300 newtons of force there. All right, now let's go to the next one here. Okay, and on this one, we've got two people pulling. Now this person is pulling with 300 newtons of force, and this person is pulling with 300 newtons of force. So what would this scale read? Well, it's going to read the sum of both of those, which would be 600 newtons of force. Well, how about if we have this situation? What is this similar to? Is it similar to situation A or situation B? Well, this person is pulling with 300 newtons of force, and this person then would also have to be pulling with 300 newtons of force. So at first it seems like this should be reading 600, but no, in fact it's just reading 300 newtons of force. Sorry about my pen there. This is really just reading 300 newtons of force. Well, why is that? Well, it's not similar to this situation. It's similar to this situation because the tree has to do an equal and opposite pull of 300 newtons of force. Okay, so when we look at this person is like the tree. If that person wasn't there pulling on it, then that spring scale would be going nowhere. Okay, so if we look back at B, the tree here is actually pulling back with 600 newtons of force on this one. Okay, so this is reading what the force is in one of the directions. Okay, just only in one of the directions. And that's a little tricky to foresee because we've got Newton's third law acting in on this problem. All right, and that's all we're going to get to for right now.